It's 3 o'clock, so let's get started again. So the midterm is up. I posted an announcement about that. So go ahead and sign up and start solving some of the problems on there. Some of you already have. Should be a lot of fun. So it would be nice to see what people can do with some of these problems, because some of them are easy, like the first few are easy, but then they get progressively a bit harder. So I'd really like to see what you guys can come up with for those. So are there any questions about the midterm? So every problem you get unlimited submissions, it keeps your highest score, all that stuff, right? And I can't actually enforce this, but you could use any programming language you want, but I prefer if you use Python, right? Because that's what we've been doing here, and it's easier, but I can't enforce that. Any other questions about it? All right. Also, just a quick recap, homework 4, assignment 4 is due next Monday. So any questions about that assignment? All right. So what we've been talking about starting yesterday was about this new paradigm of solving problems called dynamic programming. And what this idea was about was the motivation, of course, was that recursive algorithms are too slow. And why did we come up with how they were so slow? Because for some examples, we were computing values that we've already computed. So we're basically doing work twice, or at least twice as for each of those. So what we want to do is we want to make sure we only compute anything we want to compute exactly one time. And then after that, we want to make sure that we can access it for a later computation, so I don't have to recompute what I've already done. The main idea is to store previous computation in a table somehow, like represent it in some way so that I can access it later. And we went over the origin, but so the idea was that it has an interesting history of where it came from, but the basic idea is that we're going to be doing recursion, and we're going to do it in a smart way, which is storing previous computation. And so I tell you the basic way of solving any dynamic programming problem, just doing all these steps. So the main one is just doing figuring out how to split up the problem accordingly, and then save previous computation, and then return the results back to bring all the subproblems together. So the first one we looked at was Fibonacci numbers. So the way we looked at this was that we know that Fibonacci numbers are defined as the nth one is equal to the n minus 1th one plus the n minus 2th Fibonacci number. And so what we want to do is we want to be given a particular number n, and I want to calculate the nth Fibonacci number. And so what we can do is we can make a recursive algorithm. So we make a Fibonacci function n, which takes an integer n. So the base cases is if the number is equal to 1 or 2, I suppose you could make it less than or equal to 2, but if you're at one of these two subcases, then I return 1. Otherwise, then I return the n minus 1th number plus the n minus 2th number. So the basic way to do that, the only way I can do it in this example is to call myself with n minus 1 and then also call myself with n minus 2. So those are my two subproblems that I want to solve. And so how do I get the result that I want, the nth number? I just add them, because that's how they're defined anyway. So I'm actually solving the problem here. But the thing is, I'm not actually storing previous computation somewhere. So what we were able to show was that not only is the runtime really terrible, it could be exponential, so it's extremely slow. But the problem was that if we expand the runtime a few times, it turns out that we're solving the n minus 2th case twice. And then we're solving the n minus 3th case even more times, and then you see the pattern, right? So I want to be able to reduce that 2 to a 1 for every single possible n minus 2, n minus 3, all the way down. So I only do computations exactly one time. So the basic idea behind dynamic programming, but also here, is memoization, which is storing previous computation in some form. And so what you usually use is a table of dictionary. So dictionary maps inputs to outputs usually. So what we do is when we're given a particular value, say a dictionary, we look in the dictionary and extract the value out of the dictionary associated with that value, with the key. And if it's not there, then we actually do the computation, then store it in, so that we don't have to compute it at a later time. So we talked about last time, how do we store the numbers? And the way we thought was most efficient was to be given a particular number n, and then I want the nth Fibonacci number associated with n. So the data structure we used was a dictionary. We mapped this number n to its Fibonacci number, f of n. So a memoized version of the algorithm is, so this is going to be our dictionary I call memodict, and the function is defined the same way, but first I check if the number that I'm given is already in the dictionary, then I don't need to compute anything, right? I just return the value associated with it. Easy. But otherwise, then we haven't computed the value of n yet. So we're going to start doing the computation. So we have our base case. If it's 1 or 2, then we return 1 just as usual. But otherwise, I want to be able to capture the output, then save it, and then return it. Because if I just say return fib of n minus 1 plus fib of n minus 2, then I'm going to be throwing away the computation, and I'm not going to be saving it in the table, right? Because I want to be able to save it in the table for a later computation. So I want to capture it first, and then I'm going to save it in the table. So the value associated with n is now f, the computed value based on the recursive calls. And then I return the value as usual. So the only thing I do differently is I store the value in the dictionary now. And that's it. So, let's see. Yeah. So the thing is, the only reason we would do the recursive calls of n minus 1 and n minus 2 is if n is not in the table, right? So how many times am I going to be doing a recursive call for a given n? Well, if it's not in the table, then I'm going to do the computation, but then I store it, right? So I'm never going to call fib of n again, right? Because I'm never going to do that recursive call again. So we note that for every single value of n, I only do a call to this function one time, right? I'm never going to do it more than one time. And so what are the possible calls to this Fibonacci of n? Well, if we look at our algorithm, we see that right at the start, there's nothing in the dictionary, so I call fib of n. And then I go all the way down to the else case, and I see, oh, fib of n minus 1, fib of n minus 2. I'm going to do those calls, right? And then it's going to go all the way down. It's going to make a lot of calls, and then it's going to come back up with the values in the dictionary. So the only calls that could be in Fibonacci of n, since we know that every single value of n, we only call fib of that number exactly one time, we only make the calls fib of n minus 1, fib of n minus 2, all the way down to fib of 1, right? I never do any other calls. I never do any one of these more than one time, which is nice. So we have n recursive calls to make. So we know how many recursive calls we're going to make. So now all we need to do to figure out the runtime is figure out how much work I'm going to be doing per recursive call, because I know how many I'm doing. Right? So what's the time per recursive call? Well, we only have constant amount of work. And why is that? Well, looking up in a dictionary is constant time in a sense. So why is it constant time? Does anyone know why? Yeah, but how do I determine if n is in this dictionary? Well, it's just like if you want to determine the values in an array, you can do it in logarithmic time by doing binary search, right? But how do I do it in constant time for a dictionary? You can actually do it in terms of an index here. But does anyone know how a dictionary is implemented on the back end? It is actually in terms of a hash table. So the idea is we're going to hash this value of n to a unique value, and then that's going to hash to a unique index in the dictionary, in the back end of the dictionary, which is usually a list. So basically, I just look through the number, compute the hash, and then figure out if the hash is in this list. It's much more complicated than that, but it turns out we can actually do a constant amount of time to look in a dictionary. So checking if it's in memodict takes constant time. Checking if it's equal to 1 or equal to 2, constant time. Otherwise, we're just making recursive calls. So let's just say we know how to compute fib of n minus 1 and fib of n minus 2. Adding two numbers, in a sense, is constant time. Right? It's not really, but let's just assume that it is. So computing that is constant time. Storing into the dictionary takes constant time because, first of all, we know that n, when we store the value of f in there, n is not in the dictionary. Right? Because if it were, then we would have hit it at the beginning. So we know it can't be here. And we know that accessing a dictionary and storing and retrieving from a dictionary takes constant time. So that takes constant time too. So the runtime of this algorithm per recursive call is constant time. Nice. So we have constant time work per call. And how many do we have? We have order n of them. We actually have exactly n, but order n is good. And combining the solutions, doing the addition, constant time. And so the total running time is the number of recursive calls times the time per recursive call. 1 times n, I believe, is n. So we have a linear time algorithm. Does anyone remember the runtime of the naive algorithm? 2 to the n, upper bounded by, yeah. It is exponential. So exponential versus linear time is a huge difference. So let's actually do a coding demo of this. No, I don't. All right, so what I have here is our favorite time class. So basically, I have two functions that I'm going to be implementing, the naive version of Fibonacci and the memoized version. And what I'm going to be taking from the user is the integer n via sys.argv, and then I'm going to time how long it takes to do 5 iterations of each, and then figure out the average amount of time. So the naive algorithm is, first of all, we need the base case. So what are the base cases here? Yeah, if n is 1 or 2. So if n equals 1 or n equals 2, then what do I return? I return 1. Because the first Fibonacci number is 1, second is also 1. Right? Easy. Otherwise, what do I return now? Well, what is the n? Yeah.
Yeah. Otherwise, return fib of n minus 1 plus fib of n minus 2.
Yeah. So I recursively call myself with n minus 1, adding also another recursive call with n minus 2. All right. So I'm going to comment out the Memoized version. Let's just see how long this runs. So Python 3, Fibonacci, let's just say we want the 10th one. All right, so it's a really short amount of time. So let's up this a little bit, 13. All right, 15, maybe 20. All right, it's starting to take a little longer, maybe 30. Wow, almost half a second. Let's try 31. So the last running time was about half a second. So we know that this algorithm is upper bounded by 2 to the n running time. So if I up the n by 1, what do you think the runtime is going to do? About double, yeah. Good. So maybe that's what we'll see. It's a little bit less because we upper bounded it by 2 to the n. It's actually around 1.6 to the n. But yeah, we see this kind of behavior is exponentially increasing. If we increase it to 32, we will see almost another doubling in running time. which is kind of what we see. A little less, but it's about what we see. All right, so every time we increase n, we double our running time. That's not very good. So let's do our Memoized version. So what was the main thing in the Memoized version that allowed us to get a much faster running time? Store the computation in a dictionary. So I'm going to make a dictionary, which is just going to call memo. So it's empty for now, but then I'm going to be filling it as I go. So what was the first thing I needed to do here? It would check if it's in the dictionary. So if n is in memo, then I return the value associated with n. So return memo of n. Simple, what we've seen before. All right, so now I need to do my base cases and the non-base case. So I need to make my checks again, if n is equal to 1 or n is equal to 2. Then I can return 1. Why should I not, I could do this if I want. Why do I not save this in the table? I could if I want to, but I don't have to. Yeah, because I'm not going to be doing any more recursive calls here, so it's not going to branch out into more recursive calls. So the number of recursive calls will stop here anyway. So there's not much of a point to save it, but otherwise, yeah, I'll do this on a separate line. Otherwise, what do I have to do now? I can't just say return recursive call n-1, recursive call n-2, and add them. What do I do here?
Store it?
Yeah, I have to store it in the table. But if I just do return fib memo of n-1 plus fib memo n-2, well, this isn't storing it in the table, right? So what should I do with this? Well, I can't just return it right here, right? So what's another way? Well, I want to save this value somewhere. So I should store it in a variable, right? And then store it in the table. So I'm going to store it in a variable called f. So what should I do with f now? Store it in the table. So I'm going to set memo, n's value in the memo to be f. And then what do I do now? I return f, right? Because that's the value I should return anyway. So return f. All right, and that's it. So let's uncomment this and see how long it takes for 32. It should be much, yeah, that's a lot faster. So around 1.2 seconds average for naive and around 100,000th of a second for the memo version. It's just a simple change made it run, God, it's like almost 100,000 times faster. Isn't that insane? Let's up it by 1. It'll be a little more, but it won't be very much more. Almost nothing more. And yeah, and isn't that just insane how much difference exponential versus linear time makes? It just blows my mind every time. All right. Any questions on how we were able to make this? Okay. So yeah, running times, even though you may care about things like caches and order of execution, things like that, although those are really important, sometimes the asymptotic running time actually really does matter here. Comparing like an exponential time algorithm versus a linear time algorithm, that'll actually show the main difference in their running times. All right, so we talked about this. So we can actually improve this a little bit. So we're doing what is called a top-down approach. So what is that? What we're doing is we're given our top case in a sense, which is computing the Fibonacci number, the nth Fibonacci number, and then we recurse down. So we call n minus 1 over here and n minus 2 over here, and then we recursively call ourselves. And then we keep going down until we hit the base cases, and then combine our solutions, then go back up to the top. So that's what's called a top-down approach. And so it might be nice to think, well, maybe I can just start from the very bottom and work my way up to the top. And that's what's called a bottom-up approach. And so it turns out, yeah, you can. What you can do is you can store the value associated with 1 and 2 in a table, in the table. And then what I do is I call the last 2 values stored in the table, and then just keep just updating my current value as I go until I get to the one I want, which is the nth one. So I'm starting from n equals 1 and n equals 2, and then add those 2 values, and then I take the last 2, add those 2, take the last 2, add those 2, all the way until I get to n, right? And so that's what is called a bottom-up approach. You start from the base cases, and then you work your way up instead of working your way down. All right? And then return the value that you want. So what's better about this algorithm than the Memoized version we just did? Other than thinking about it differently.
Less recursive calls?
There's actually no recursive calls here, right? Because I'm just iteratively checking the last 2 values in the dictionary. What's also much better about this algorithm?
You're not using up as much storage.
I actually will be here, but because I'm going to be storing all those values. But do I need to? No. Right, I only need to keep the last 2. I can forget about every other computation I did, other than the last 2, right? So I only need to remember 2 numbers here instead of n numbers, right? Because once I get up to n, I don't care about 1, 2, 3. I only care about n minus 1 and n minus 2. So I only need to keep track of 2 numbers at a time. So what's better about this? I only need to keep track of 2 numbers, so it's constant storage and the same running time, because I'm doing n additions here. So this will run in O of n time. And the Memoized version had an O of n space usage because I'm storing n numbers, well, O of n numbers. And here I'm actually doing constant storage because I only need to remember 2, actually 3, but I only need constant number here. Okay? So any questions about how we were able to formulate all this? All right. Anyone sick of graphs yet? It's because we're going to go into more graph stuff. So that autobiography I mentioned last time, which talked about the origin of dynamic programming, that was from Richard Bellman. So that's one reason why he's really famous. But another reason he's really famous is his algorithm. So Dijkstra had his algorithm for single source shortest paths in weighted graphs, right? So the reason we came up with Dijkstra's algorithm was, well, we didn't come up with it, but we discussed it. The reason we discussed it was that sometimes we want weights in graphs, right? And we want to find the shortest paths in those graphs. But breadth first search and depth first search did not take those into account. So Dijkstra kept the minimum of the shortest distance for each vertex as we go along, and then just keep updating the minimum as we go. So this algorithm also does single source shortest paths in weighted graphs, right? So note, this does not say simple path, it says path. So what's the difference between path and simple path? In a sense, yeah, you're almost there.
A path isn't allowed to cross over itself.
Yes, so a path is just a sequence of vertices, right? Simple path is one that doesn't repeat any vertices. So a simple path doesn't have any cycle in the graph, whereas a path can have cycles, right? So let's think about why we can't, so that'll be helpful in a second. So why don't we just use Dijkstra's algorithm here? What do you think is a problem with Dijkstra's algorithm? I mentioned it last time.
Negative numbers?
Exactly. The Dijkstra's algorithm does not work with negative edge weights. And it's just a simple exercise, but the way Dijkstra's algorithm works is if you have negative edge weights, it may choose one that's locally optimal, like it's really good to go along this path, but this other path, which starts off bad but has negative edge weights along the way, which does have a shorter distance, it won't pick that one, right? So it turns out Dijkstra's algorithm does not work in general with negative edge weights. Yeah.
Quick question. What would be the purpose of negative edge weights?
You could think of that, it could be formulated in a lot of ways, but you can think of that maybe in terms of elevation change, on like a road or something. So like a negative weight on an edge means going down. Or maybe, it's hard to think of cases, but maybe you can think of it as like a stock, for example. Like if you went along this edge, the stock drops or something. That's actually not a good example, but there are graphs where you do actually need negative edge weights, and you still want shortest paths. But it turns out you can't use Dijkstra's algorithm. So what Bellman-Ford and although Moore is kind of like the person that everyone forgets. It's always called Bellman-Ford. Moore is always forget. So I kind of wanted to honor him here. But anyway, so Dijkstra doesn't work with negative edge weights. So if there's a negative weight cycle, so what does that mean? There's a cycle, and if you add up all the edges along the cycle, it's a negative number, right? So I claim that there's no shortest path between the source and the associated vertices. So why is that? We actually just discussed it. It's single source shortest paths, not simple paths, right? So if there is a negative weight cycle, then since I'm doing paths and not paths and not simple paths, then I can just go along that negative cycle as many times as I want, keep getting a smaller negative number, right? Because is there a smallest number? No, so I can just keep going along here as many times as I want. And so therefore, there really is no shortest path here, right? But I still want this, right? So what we can do is we can find the shortest paths in this graph with negative edge weights. But if there's a negative weight cycle, then I just say no, there is no shortest path, right? Because if there is a negative weight cycle, then I can't find the shortest path anyway, right? So negative weight cycle, I can just throw my hands and say no problem. So this is called the Bellman-Ford algorithm, although it should be Bellman-Ford-Moore. But the key here is that if we do not repeat vertices, so it's a simple path in a sense, the longest one uses n-1 edges. So why is that?
Because they were all connected, we only have up to n-1 edges.
Well, I'm talking about paths here, not connectedness. So think about it. 2 vertices, 1 edge. 3 vertices, the longest one is 2 edges, right? So that I don't repeat one, right? Yeah, so n, there's going to be n-1 connecting in between, right? So this is actually going to be the key for this algorithm. Any questions for what we're trying to solve here? All right, so the main algorithm here, so I'm going to call it Bellman-Ford with a graph G. And what W is a function, in a sense, where you give it an edge and it returns you the weight on that edge. So I assume I can do that in constant time, maybe like via some table or something like that. But it's going to be a function that returns to me the weight of an edge. And S is obviously going to be the source vertex where I find the shortest paths. So I'm going to, again, have this distance list, which will keep track of the shortest distance to all other vertices, right? So right at the start, the distance from S to itself is 0. And the distance right at this point is infinity to everywhere else. I don't know if I can reach there. I'm just going to say they're infinity at the start and then update it as I go. So the reason that we have this note that the longest path uses n minus 1 edges is that I'm going to be doing relaxations, as it's called, on edges. So, relaxations on the vertices. So the vertex says I'm distance 100, right? And then I'm going to keep updating that n minus 1 times at least, because I don't know what the graph structure is, but I'm just going to make sure that I'm going to keep going until I have at least n minus 1 iterations of relaxation. I can do more if I want to, as you'll see in a second, but n minus 1 at least, to guarantee I get every single path, right? Because I actually don't need to do any more, because there's no paths that repeat vertices longer than this. So this is the longest I need to run for. So I'm going to repeat the following, the number of vertices minus 1 times. So it's basically like Dijkstra here. I'm going to be doing relaxations on this distance for the vertices. So for every single edge, I'm going to do this relaxation. So for every single edge, the distance to V, the vertex that I'm currently looking at, is going to be the minimum of whatever it was, and also the minimum of that, and the distance to U plus the weight of this edge, right? So it's basically like Dijkstra again, in a sense. So I'm going to be doing this relaxation over and over and over until I get, I do this V minus 1 times. Yeah.
What do you mean by relaxation?
Yeah, this minimization thing, like doing the min function, that's called relaxation. So like I potentially could be lowering this over and over and over until I actually get the smallest distance, right? Cool. What?
I just wanted to make sure.
Yeah. Mm-hmm. All right. So what we have here is that we have the minimum distance for every vertex. So now we have this, but I want to make sure that there are no negative weight cycles. Because if there are negative weight cycles, then I should just say, no, you can't actually do this. So I need to detect if there's a negative weight cycle here, right? So what do? I look on every single edge, right? And I make this check. So what does this say? So I look at every single edge that exists in the entire graph, and I say, if the distance to V is longer than the distance to U plus this weight, right? And if I make that check, it's a negative weight cycle. Yeah, because if it's longer than this, right, then then that means that the weight of UV must be negative, right? Because if this weren't true, then we would have made the minimization of we would have made d of v equal to d of u plus the weight of uv, right? We would have made that check earlier, but we didn't. So we must have a negative weight cycle here, because and another thing is that the weight of this edge uv must be negative, because why is that? Yeah, because this check can't happen unless there's a negative weight cycle, because if there were a negative weight cycle, we would have relaxed all of the vertices along it, except for this vertex V. So if it's at least there, then we must have this property that the distance to V is at least the distance of d of u plus the weight on that edge. Okay? Are there any questions about that? I know it's a little bit confusing, but the main idea is just to relax these edges over and over and over until you get to the point where you must have relaxed it the maximum number of times. You can do it more if you want, but you don't have to. But the whole point is that if you have this property, then you must have a negative weight cycle. So therefore, we just return false in that case. But if that's not true for every single edge, then we return the distances themselves. All right, so this works for negative weight edges because we just update distances as we need to. But the only thing we need to check for is if there's a negative weight cycle. All right, so analysis of this. We detect if a negative weight cycles in the last iteration. And then, so let's look at the initialization. So we set the distance of each vertex to be infinity for every single vertex other than S, and S's distance to 0. So therefore, initialization of these distances takes linear time in the number of vertices. So we do this repetition step. We repeat number of vertices minus 1, so that's order number of vertices times. And each time, we're going to be looping through every single edge in the graph. So every time we do an iteration of this outer loop, we're going to do O of the number of edges work. So this loop right here is going to run in V times E time, instead of in terms of breadth first search, where we had V plus E time. Because in that case, every single edge is going to be examined only at most twice. So here, we're going to actually have a V times E algorithm instead of a V plus E algorithm. So the runtime actually goes much less here because potentially we actually need to make these checks. We actually do need to repeat V minus 1 times, and we do need to check every single edge because we don't know the graph's property, the structure of the graph. All right? Are there any questions about Bellman-Ford? All right, so I'm not going to do a demo, but if you look at the documentation, there is a function in Network X that actually allows you to do this. So it's called Bellman-Ford, and you can assign weights to all edges in a Network X graph, and then you just can call Bellman-Ford, and it returns to you. Actually, it returns you more than what my algorithm does. It returns to a predecessor list and a distance list. So the distance is what I described before, but predecessor says what vertex found me, so that if I travel along that way, I get to the source as quickly as possible. So it's like how the shortest paths were determined. So it's kind of like the breadth first search tree that we did a few times ago. So it's this tree where you start from the source vertex and you go out in the graph. So here is just a predecessor of where you were found. All right? So I know I wouldn't want to implement this algorithm by myself, so NetworkX has this functionality for you. Okay? Any questions on Bellman-Ford? All right. Let's do one more. So another algorithm, which is called Floyd-Warshall. Maybe when you're trying to analyze a network, you say, well, I pick some vertex to start with, and I find the distances from this vertex, right? But that picking of that vertex was pretty arbitrary, right? Wouldn't it be nice to be able to figure out those shortest distances from every vertex in the graph? So what we can do is, essentially, we can do single source shortest paths like Bellman-Ford or Dijkstra or even breadth first search from every vertex. So we start from one vertex, do the computation, then try the next one, do the computation, etc. So essentially, we can just multiply the running time of each of those by the number of vertices, right? So if we look at Bellman-Ford, it would just be V squared times E running time. So what is, so let's just try to make the O notation easier. So V squared times E. So what is E in terms of number of vertices? What is the upper bound on the number of edges that there could be for V vertices? Not in a complete graph. In a path, you're right, but in any arbitrary graph, how large could it be? Well, every vertex, as you said, could be connected to v minus 1 other vertices, right? So the number of edges could be the number of vertices squared, or order, vertices squared. So v squared times potentially v squared. This could be a v to the 4th algorithm for doing these single source shortest paths from every vertex. So I guess a quartic now time algorithm, that seems pretty slow, right? N to the 4th, that's pretty bad. So what all pair shortest paths is what it's called. So what this algorithm does is it reduces this 4 to a 3. So instead of a quartic running time, we have a cubic running time, which is still slow, but it's definitely a lot better. So what we can do naively is just do it from every single vertex, and then multiply it by v. If we have a non-negative edge, actually that should say negative edge weights. Yeah, if we have negative edge weights. Yep. Finding mistakes in my slides. All right, so if we have negative edge weights, as we described, we can use the Bellman-Ford algorithm. But as we said, this could take number of vertices to the 4th time. And can we do better? We can reduce it to cubic running time using dynamic programming. So what we'll be doing is we're going to be doing a lot of relaxation in the graph, right? And what we're going to do is we're going to store it in a giant table. So we're going to sacrifice storage here for faster running time. So it's a nice trade-off here. And there's a conjecture that you cannot solve this problem any faster than this. So this is optimally the fastest you can do. It's not quite, in a sense it is optimal, in another sense it's not. But you can't reduce this 3 to anything like 2.99999 or anything like that. You can't do anything less than 3. All right. So let's think about paths in a graph. So let's say that we had some path from vertex I to vertex j, and we add up all the edges along the way. And it has weight wij. So I'm going to denote w with 2 vertices to mean the total weight along the shortest path from the first to the second vertex. And let's just say we had another one that passes through this intermediate vertex k, which has wik plus wkj weight, right? So either they're both the same or one is shorter, right? So we have 2 paths with possibly 2 different weights. So if this straightforward path, wij, is longer than going through this immediate vertex, right? Then this path that goes to this immediate vertex is shorter, because this one's longer than this one, right? So basically, we can update this distance at the top to be the wik distance plus wkj distance. So just update it. So we're doing a relaxation here. So we update, if this condition is true, we update wij to be equal to wik plus wkj. And then all we need to do now is just update every single pair of vertices in the graph, and then, so we loop through all vertices for I, all vertices for j, and then possibly looking through every single immediate vertex for k, right? Because every single path, although it doesn't have to, but most paths must travel through another vertex, right? So what we're going to do is we're going to loop 3 times through the number of vertices, 1 for I, 1 for j, and 1 for this immediate vertex k. And then we do relaxations over and over and over and over until we exhaust all the possibilities. So it's basically just running through all the possibilities here. Since we're storing the distance for I and j, so all pairs of vertices, I need to keep a vertices times vertices size matrix. So it's a 2D array where the rows are indexed by, say, I, and the columns are indexed by j. So I look in row I and column J for the value that I want. Okay? Anyone confused on what we're trying to do here? Okay. So the algorithm is, all we're doing is taking a path, we're taking a graph G, and we don't need a source vertex because I'm going to return to you the single source shortest, I'm returning all the shortest paths from all vertices. So I don't have a vertex S here. So I'm going to initialize my array where I'm going to be storing these shortest distances, and I'm going to set them all to infinity at the start, and then I'm going to progressively lower them as necessary. So for all vertices V, the distance from V to itself is 0. So that's just initialization. And we're just going to basically run through the graph one time to initialize the weights of of all the edges. So for every single edge UV, I set the distance from U to V to be the weight of that particular edge. So it only concerns the vertices that are one apart from each other, but it doesn't concern, say, I and J if there are two if they are two edges apart, right? It only concerns one apart. So what we're going to be doing then is we're going to be trying to update those distances and lower them accordingly. So we're going to loop, have 3 variables here. So I is going to run from 1 to the number of vertices, J is also going to run from 1 to the number of vertices, and K 1 to the number of vertices. And each of these is independent. So the reason I write it this way is that I don't want 3 separate indentations here, so it makes it easier to read. But we're going to have basically 3 for loops here that loop through every single vertex. So basically, it's just a relaxation as before. So the distance from I to J is going to be the minimum of what it was before, and the distance from I to K, the immediate vertex, and K to J, adding them together. So it's just doing a relaxation over and over and over until I exhaust every single possible choice of 3 vertices here. Okay? And then I just return the array with all the distances in it. Okay? Any questions on that? Okay. Yeah, a lot of these algorithms are just basically doing minimizations and storing into a matrix in some way. So we have 3 loops that iterate the number of vertices times. So this is a cubic time algorithm, right? Because I goes from 1 to V, J goes from 1 to V, K goes from 1 to V, independently of each other. So therefore we have V times V times V iterations here. So it's V cubed. So we have basically a cubic time algorithm. And this is believed to be the best possible. What if there are negative weight cycles, though? This algorithm does work with negative edge weights, but what if there are negative weight cycles? Well, if there's a negative weight cycle, just pick a vertex on that cycle, and so therefore the distance is less than 0. Why? From that vertex to itself is less than 0. Why? Because we went around the cycle and we updated the distance. So basically, if there is a negative weight cycle, say from vertex I and it goes to K, other vertices up to I, so it's a cycle. If it's negative weight, the distance should be 0 for every single vertex to itself, right? Because that's what it means. I'm not traveling anywhere, so the distance is 0. But if any of them are less than 0, then we have a negative weight cycle. Because we're updating distances, and we just found a shorter distance to get from I to itself than 0, which doesn't make any sense, right? So therefore, if this condition's true, then we found a negative weight cycle. So essentially, we are doing exactly Bellman-Ford for every single vertex and saving a factor of the number of vertices here. And we're doing exactly the same thing. we can handle negative edge weights, and we can handle negative weight cycles all in the same boat, which is kind of awesome. So if this is true, we can say there's a negative weight cycle. Any questions on that? All right, so I just want to point out that there are a lot of functions here that do basically the same thing. So all pairs shortest path, all pairs shortest path length, all pairs Dijkstra path. So there are many functions that do this functionality, but the algorithm is pretty simple. Just loop through every single vertex for I, j, and k, and then update the distance of I to j using this minimization thing. It's pretty simple. Any questions about that? All right, let's take a break. We're back. So any questions on what we've covered so far? So we've seen a few dynamic programming algorithms, one for Fibonacci numbers and then two more for graphs. So I don't know about you, but I think we can use a break from graphs. So we're going to start doing some algorithms that aren't related to graphs. So the first one is called the knapsack problem. So how many of you have heard of this problem? Okay, someone has. So the knapsack problem is, so imagine you're Indiana Jones. So you're right, it is Indiana Jones. And basically you're going to some tomb, let's say, and you want to carry a lot of valuables with you, right? But the problem is that you're carrying a back. In this case, is he wearing crutches? No, he's not wearing crutches. Never mind. You're carrying a backpack, and obviously you're a human. You can't take infinite weight or infinite amount of stuff with you, or unlimited in this case. So what you want to do is you want to be able to fill your backpack with as much as you can, but also maximize the value of the stuff you put in, right? So let's just say we have a bag like this, which can hold a certain amount of weight or a certain amount of volume, let's say. And each of the items you could take with you has a certain weight attached to it and a certain dollar amount or value associated with it. So you may think, well, that item over there is really terrible, right? Because it has a lot of weight, but not very much value. Whereas like the ones over here, they have they're much better, right? Or even this one's even better. The weight is small, but they have a larger cash value associated with that weight. So the knapsack problem is I want to choose a certain number of these such that I don't exceed the weight or the capacity of my backpack, but also maximize the amount of money I can get out of this. Okay, so that's the knapsack problem. So there are other versions of this where you can break each of these into components of the same size. So you can think of that like you can cut this one into two pieces with $2 in each part and 6 kilograms in both pieces. But we're going to deal with the problem which is called the 0-1 knapsack problem. So either you take all of the item or none of the item. So you can think of that like for valuables that Indiana Jones says you can't really cut diamonds or something like that. So, what? Exactly. So, called the 0-1 knapsack problem. So more formally, we're given two lists. So we're given a set of values, which are also called rewards for each item. So this V list will have for each item the value associated with item I. And W of I correspondingly is the weight of item I, right? And what we are also given is this weight of the backpack, or more formally just some fixed constant W, a big W here. And what we want to do is we want to pick some of the elements such that the sum of their weights in this W list does not exceed W's, but it could be equal if you want, but it can't exceed it. But the sum of the corresponding elements in the V list is maximized. So that's what we want to do here. So what's a brute force way we can do this? try every possibility. So how many possibilities could there be here? Oh, much bigger. So I'm picking, you can think of this as the first element, either I pick it or I don't. Second element, either I pick it or I don't. Third element, I pick it or I don't. How many choices for every element?
2.
So 2 times 2 times 2 times 2 to the n, yeah. So I could do every single one, try every possibility. That's totally possible. It actually is not even, as we'll see in a second, it's not even known if there's a polynomial time algorithm for this. We don't know if there's less than exponential for this yet. But we'll save that for when we get to it. But we could try every possibility. So what we can do is try every single possible subset, which is easy to do. And then for each one, we compute the value of W, the sum of their weights. And if it's less than the maximum weight we can have, then I maintain the maximum value so far for each of the subsets. And then just iterate through every single subset and keep the one that has the maximum value, right? We know how to do this brute force. So can we do better? And of course we can. So what we're going to do is we're going to maintain a matrix. So most of these problems are just keep a matrix or a list or something like that. And what we're going to do is we're going to have n rows and W columns. So this n corresponds to the number of items that we could possibly take. So it's the number of crystals that Indiana Jones can take. And this big W is the maximum weight we could possibly have. So that fixed constant we're given. And so the element, the ith row and the wth column corresponds to the max value that you can pick from the first I items with weight at most W. So some subset of this first I items in the list, not necessarily all of them, but the first I, the maximum I could pick from this subset, so I pick some of the elements in here, such that the total weight is less than this little w. Everyone see what I'm trying to say here? Anyone confused? So it's kind of like a smaller version of the problem. I'm saying the maximum I can pick from these I items such that their total weight is less than W, less than or equal to this little w. And I maintain, so this w, this little w, can range from 1 to big W. So I'm going to maintain each one of those possibilities. Okay? And then what we can do is think about how we can express some of the elements in this matrix in terms of other elements. So let's think about why this is true. If we look at the first 0 items, and for any possible weight from 1 to big V, why is it 0? If I pick no items, I don't have any value. Yeah, that's entirely obvious here. Let's see. So if the weight of the ith item is larger than W, this little w, then I can't possibly include it in this first item list. So I can just effectively remove it from here. So I don't think about big W for a second. Think of this little w. I want to maintain what I can keep from the first I items such that their total weight is less than little w, right? But if the ith item weighs more than little w already, then I can't include it, right? Because it already weighs more, right? So therefore, I only need to now consider the I minus 1 items, right? So it's equal to I minus 1, and also of w. But otherwise, so we have wi is less than or equal to little w. So I want to keep the maximum value that I could possibly keep because each of these entries in this matrix is the maximum value I can obtain. So either I don't include this item or I do include this item, right? So I'm just going to include both possibilities, right? So what I'm going to do is either I don't include the item, which means I go to this I minus 1 again. So it's either going to be the maximum of just looking at the I minus 1 items, or what I can do is I look at the I minus 1 items, and then I subtract the weight of this item, but I add the value to it. Does that make sense? All right, so I keep the maximum for each of these I and W's as we go along. And then what we can do is we can fill this matrix bottom up. So we start with that first case, the 0W equals 0, and then we keep adding, we keep doing this max function over and over and over. So the algorithm is, we're given this list of values, V, and the associated weights, W, and this fixed constant, big W, which means I can't exceed this in total. So I'm going to let n be the length of V, or of little w if you want, but I'm just going to let it be len of V. And then I'm going to make this array, where it's indexed by rows being the number of elements and the columns being 1 through this big W, just as we did before. So the initialization says that if we look at 0 items, no matter what weight we look at, the value we get out of it is 0. So it's just initialization. But from I equals 1 to n, so we're basically going to be going through each of the items and then looking at weights as we go along. So we're starting with the first element we could choose from and then going through all its weights. The second item, going through all its weights. Third item, going through all its weights all the way through. So essentially we're doing a row traversal of the matrix. It actually doesn't matter how we traverse the matrix, but row is easiest here. So if it turns out that this element that we're looking at, I use I minus 1 here because of indexing, because arrays index at 0. But this, from what it was over here, this means m of I. But it's essentially the same thing. So if the element that we're looking at in the list is larger than the current weight I'm considering, then I can't possibly include it, right? So I must go back 1. So it's equal to whatever if I didn't include that element and just include the I minus 1 elements, right? But otherwise, then we do the maximum of either not including it or including it. And then we just add the value of whatever it was. Yeah.
Sorry, why do we add the value again?
Because oh, okay, yeah. So what this really says is either I don't include this element, or I only include this element, and I consider whatever, either I do include it or I don't include it. So if I do include it, then I add the value of whatever it was over here.
Okay.
Yeah, so whatever it was over here, add the value of whatever it was here. And then I keep the maximum of the two, whatever it is.
I see.
Okay? So it's just a simple implementation of what we did. All right? Any questions on how this algorithm works? All right. So what's the runtime? Anyone want to shout it out? Let's look at it again. So
Naive was 2 to the n.
the naive was 2 to the n, yeah. So what's the runtime here? Well, making an array, you can think of that as constant time, or maybe n times w, however you want to think of it. But certainly the loop scenario, we have n iterations of the outer loop and big W iterations of the small loop, right? So therefore, we have n times w runtime. So therefore, the runtime is n times w. Pretty simple analysis. This is efficient.
No, not for bigger.
Well, it's in terms of this it's in terms of W, right? But how are we given W? It's a number, right? So how are numbers usually written? Say in like a modern computer.
You mean X?
Or like some written in some base, right? Binary, something like that. So if I have a number W, it has value big W. How many bits do I need to store that number? A what? Not necessarily. Order, let's say. It goes back to the example we talked about I think like 2 or 3 weeks ago, where I told you the big lie you've always been told. Algorithms are in terms of the size of the input, not in terms of the value. So what is the size that we need to store big W? Well, let's see.
You mean like 64, but like how the numbers?
Well, how many bits do I need to store the number in terms of big W? So let's just say I wanted to write down the number 1024, for instance. How many bits do I need to write that down? Well, it's 2 to the what power, if you remember?
8 or 9?
It is 10. So, but essentially, what is the O notation in terms of big W to get to the size of what you need to write down? Does log base 2 jump out to anyone? So essentially, whenever we want to write a number down or give a number to someone, we're giving them order log the number of bits, right? We're not given big W bits. We're given log, essentially, of big W bits. So we really do have n items here, but we're given log of big W. So the size of the problem that we're given is n plus log of big W. But the runtime is in terms of n times big W, not log big W. So this algorithm is not efficient, right? Because, and another thing is that W is unconstrained in terms of n, right? So W can be extremely large in comparison. So you can make W very large to make the algorithm as slow as you want. So what this is called is called a pseudo polynomial time algorithm. It's not a polynomial time algorithm. And so we also need to store that matrix with n rows and W columns. So we need order n times big W integers. So that's not an efficient space algorithm either. So this algorithm is just bad in every way. But it turns out we don't even know if there's an efficient algorithm for this. And if you actually do find an efficient algorithm for this problem, you will be the most famous computer scientist to ever live on this earth. And once we get through these slides, I'll actually tell you why that's true. But for now, we actually don't know if there's such an algorithm for this. And most people believe that there isn't one. It's actually based on thousands of known problems that we are not sure whether there is a polynomial time algorithm or not. And if one algorithm has a polynomial time algorithm, all of them do. And that's what's called NP completeness, and we'll get to that soon. But for right now, are there any questions about Knapsack? So dynamic programming is not necessarily going to work for every single problem. It's not going to get, what am I saying? It's not going to give us an efficient algorithm for every single problem, but it's going to give us a more efficient algorithm for some problems. And sometimes, like in terms of like all pair shortest paths, we gave up more space, but we got less runtime. So sometimes there's a trade-off there. But essentially here what we have is a pseudo-polynomial time algorithm. All right. Any questions about that? I'm going to leave it there, so I'll see you tomorrow.